I'm Markarinis, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 23. We've discussed perfect numbers before. A perfect number is a number which is equal to the sum of its proper divisors. So, for example, 6 is a perfect number, since its proper divisors are 1, 2, and 3, and 1 plus 2 plus 3 is 6. The second perfect number is 28. Its proper divisors are 1, 2, 4, 7, and 14, and 1 plus 2 plus 4 plus 7 plus 14 is equal to 28. Now we consider the other cases. Let n be our number, and d of n be the sum of proper divisors of n. If d of n equals n, then we call n perfect. If the sum of proper divisors d of n falls short of n, then we call n deficient. And if the sum of proper divisors d of n exceeds n, then we call n abundant. This problem is going to focus on abundant numbers. The problem description claims that every number above 28,123 is expressible as the sum of two abundant numbers, though not necessarily distinct abundant numbers. Hence, there is a finite collection of numbers not expressible as the sum of two abundant numbers. This problem challenges us to find the sum of all such numbers. Before we dive in and start coding, let's talk for a minute about why this collection is finite. After all, if there's an infinite number of these numbers, then it's not really meaningful to add them all up, so why is it that, beyond a certain point, every natural number can be written as the sum of two abundant numbers? We'll need to understand a few properties of abundant and deficient numbers in order to get there. Consider an arbitrary natural number n, and imagine that we multiply that number by some other natural number c greater than 1. I claim that the sum of proper divisors of cn is strictly greater than c times the sum of proper divisors of n. I promise I'm going somewhere with this little lemma. We can write out d of n as the sum of n's proper divisors. If we multiply both sides by c, we get a true statement that results from summing a bunch of multiples of c. We'll call this sum star. Now let's do the same for the left-hand side, d of cn. We can write out the divisors of cn just like we did before, which sum equal to d of cn. We'll call this sum double star. Every term of the sum star appears in double star. Let me put that another way. The terms of star are the proper divisors of n, each multiplied by c. And if you take a number which divides evenly into n, and you multiply it by c, then you get a number which divides evenly into cn. Since every term of star appears in double star and all terms are positive, it follows that double star is greater than or equal to star, since double star consists of all the terms of star and potentially some more. Further, there will always be strictly more terms in double star. The number 1 must be a proper divisor of cn, so it appears in double star, but it's not a multiple of c, so it cannot appear in the equation star. Hence, double star is strictly greater than star, so d of cn is strictly greater than cd of n. This one lemma tells us several neat things about abundant and deficient numbers. For instance, if you have a perfect number, then we know d of n equals n. Hence, any multiple of that perfect number must be abundant, since d of cn is greater than cd of n per our lemma, which is equal to cn since the original number n is perfect by assumption. So the sum of divisors of cn is strictly greater than cn itself. We can go the other way too. If cn is a perfect number, then d of cn equals cn. So cd of n is less than d of cn, which is equal to cn since cn is a perfect number. Divide both sides by c and we find that n is deficient. So all of the proper divisors of a perfect number are deficient. In summary, if you have a perfect number, then all of its non-trivial multiples are abundant, and all of its proper divisors are deficient. We can use similar logic to conclude that if you have an abundant number, then all of its multiples are abundant, and if you have a deficient number, then all of its factors are deficient. Now, we want to prove that every sufficiently large number can be written as the sum of two abundant numbers. The problem description tells us that every number greater than 28,123 can be represented in this way. But I'm actually going to prove a slightly different limit. I claim that every number greater than or equal to 27,948 can be written as the sum of two abundant numbers. To do this, we're going to need two magic numbers, 88 and 315. These two numbers have some special properties that are going to come in handy for us. The sum of proper divisors of 88 is 92, so 88 is an abundant number. This means that, per our earlier lemmas, every multiple of 88 is also abundant. The sum of proper divisors of 315, on the other hand, is only 309, which makes 315 a deficient number. None of our lemmas tell us anything about the multiples of a deficient number. All we know is that the factors of 315 are deficient. However, in the particular case of 315, we have the property that the first 88 multiples of this number are abundant. That is, 315 times 2 is abundant, 315 times 3 is abundant, and so on, up to and including 315 times 89. We can write a computer program to verify this easily, since it's only a set of 88 numbers. Here's how we might do this in JavaScript. Checking whether a number is abundant or not simply involves iterating over all the proper divisors of the input and keeping a running sum. Then we return whether the running sum is strictly greater than the original number n. Remember that this is a strict inequality. If the sum of divisors is equal to n, then the number is perfect, not abundant. Then our main code simply needs to call this function for each multiple of 315 we care about, and we have our verification. That being said, we can also verify this property analytically without resorting to a brute force computational check. The claim is that for k from 2 up to 89 inclusive, the number 315k is abundant. Let's see how to prove it. First, we can knock out several of our multiples by observing that 3 times 315, 5 times 315, and 7 times 315 are all abundant numbers. By our earlier lemmas, every multiple of an abundant number is abundant, so any multiple of these numbers is abundant. That means that if k is divisible by 3, 5, or 7, we know 315k is abundant. So from now on, we can assume that k is not divisible by any of those numbers. Let p be a prime number which divides k. Since k is not a multiple of 3, 5, or 7, we can assume that p is not 3, 5, or 7. I aim to show that 315p is an abundant number, and since 315k is a multiple of 315p, the former must also be abundant. Now there's a reason we eliminated the cases of 3, 5, and 7 specifically a moment ago. The number 315 has prime factorization 3 times 3 times 5 times 7, and p is a prime number not equal to 3, 5, or 7. So 315 and p are co-prime or relatively prime. That is, they don't have any prime factors in common. We've talked about some neat properties of coprime integers before. If we have two coprime integers a and b, then the factors of a times b are exactly the factors of a multiplied by the factors of b. Write sigma of n to denote the sum of all factors of n. Note that this is different from d of n, which we've been using earlier. D of n is the sum of all proper factors of n. The only improper factor of n is n itself. So in general, we have that d of n equals sigma of n minus n. Now, if a and b are coprime integers, we have that sigma of ab equals sigma of a times sigma of b, since the factors of the product a times b are exactly the products of the factors a and b. And 315 and p are coprime, so that means sigma of 315p is equal to sigma 315 times sigma p. Now consider the quotient of sigma 315p divided by 315p. The numerator consists of a sigma of two coprime integers, so we can split it into a product. We can calculate sigma 315 by direct computation. The sum of all divisors of 315, including 315 itself, is 624. We also know the value of sigma p. P is a prime number, so its only divisors are 1 in itself. So the sum of its divisors is 1 plus p. After reducing the fraction, we get 208 times quantity 1 plus p divided by 105p. Now we simplify a bit. We can split the fraction up and cancel off a p. Now, by assumption, our starting multiplicand, k, was less than 90. And p is a prime factor of k, so p must be less than 90. Thus, 1 over p is greater than 1 over 90. We've eliminated all of the variables, and this fraction is 1352 over 675. I don't really care about the exact value of this fraction. All I care about is that it's larger than 2. That is, sigma 315p over 315p is greater than 2. So sigma 315p is greater than 2 times 315p. Sigma of 315p equals d of 315p plus the improper fraction of 315p itself. So in the end, we find that d of 315p is strictly greater than 315p. That is, 315p is abundant, so 315k is as well. That was a bit of a long-winded argument, so let's review what we learned. 88 is an abundant number, so all of its multiples are abundant as well. 315 is not abundant, but for k from 2 up to and excluding 90, 315k is abundant. We verified this computationally as well as analytically, and we're going to use these two magic numbers to prove that every number greater than or equal to 27,948 can be written as a sum of two abundant numbers. There's one other property of coprime integers we'll need here, and I'm not going to prove it because the proof is a bit technical. For those interested, I'll provide a link to an online proof in the video description. If a and b are coprime integers, then every number greater than or equal to a minus 1 times b minus 1 can be written as the sum of non-negative multiples of a and b. That is, beyond a certain point, every number can be written as sa plus tb, where s and t are non-negative. Proving this isn't too difficult, but it's a bit of tedious arithmetic, so I won't be going through that proof today. Now, consider our two magic numbers, 315 and 88. 315 is equal to 3 times 3 times 5 times 7, and 88 is equal to 2 times 2 times 2 times 11. 315 and 88 are coprime, so any number greater than or equal to 314 times 87, or 27,318, can be written in the form 88s plus 315t, where s and t are non-negative integers. This is promising, but it doesn't quite tell us what we need to know. Our goal is to write every sufficiently large number as a sum of two abundant numbers. All multiples of 88 and certain multiples of 315 are abundant, but we have to deal with the boundary cases. If s equals 0, t is less than 2 or t is larger than 89, then we don't know for sure that both of these numbers are abundant. First off, we can shift our bounds a bit. Every number greater than or equal to 27,318 can be written as 88s plus 315t, where t and s are non-negative. Let's add 2 times 315 to everything I just said. So every number greater than or equal to 27,318 plus 2 times 315 can be written as a sum 88s plus 315t, where s is greater than or equal to 0 and t is greater than or equal to 2, simply by adding 315 times 2 to our previous representation. And 27,318 plus 315 times 2 is 27,948, our original bound. Furthermore, if t is greater than or equal to 90, then we can pull out an 88 times 315 from the 315t part and put it in the 88s part. We can do this as many times as we want, making t smaller in units of 88 by making s bigger in units of 315, until we get a value of t less than 90. And since we're moving in units of 88, our final value of t will still be greater than or equal to 2. So in the end, we have an arbitrary number n greater than or equal to 27,948, and we've written it as n equals 88s plus 315t, where t is greater than or equal to 2, and strictly less than 90. We proved a moment ago that 315t is an abundant number for t within these bounds. If s is non-zero, then 88s is abundant, and we've written n as the sum of two abundant numbers, meaning we're done. The only corner case left is the one where s is exactly equal to 0. That is, the case where n is a multiple of 315. N is greater than or equal to 27,948, and t is less than 90, so there's actually only one possible value for n. If t is 88 or less, then n is 27,720 or less, which is smaller than our bound. So t has to be 89, and n must be 315 times 89, or 28,035. So write 28,035 as 2 times 315 plus 87 times 315, a sum of two abundant numbers. That was the final corner case we had to address. With that, we've successfully written every number greater than or equal to 27,948 as a sum of two abundant numbers. Now that we understand why this collection of numbers is finite, let's write a program to sum them. We've already done half of the work when we wrote our isAbundant predicate a moment ago. IsSumOfAbundant takes a number and returns true if it can be written as the sum of two abundant numbers, or false otherwise. There's no fancy tricks here, we just brute force every possible addend from 1 up to n, and return true if we find a match. Finally, our main program, likewise, is simple brute force. Iterate from 1 up to 27,948, and add up all the numbers which are not sums of two abundant numbers. Finally, print the result. This isn't good enough. It's probably correct, but it's prohibitively slow. Fortunately, we can introduce caching. We check isAbundant for the same numbers all the time, so let's introduce a cache on isAbundant. We declare a variable called AbundantNumbersCache, which is initially an empty object in JavaScript. JavaScript's object model is somewhat similar to Lua's, so what JavaScript calls an object is what Python would call a dictionary, as well as what Python would call an object, rolled into one. Inside our isAbundant function, we check whether the value is present in the cache and short-circuit out if we already have a result. If not, we make sure to store the result in the cache before returning for later use. Now we've got a working solution. This program runs in about 2 seconds and gives us our answer. Before we move on, I'd like to add that JavaScript, since the 6th edition standard of ECMAScript finalized in 2015, provides an additional way to store data in a dictionary-like fashion. In addition to the more traditional map as object approach that JavaScript has always allowed, ECMAScript 6 provides an explicit map data type built specifically to be used as a dictionary, not an object. The map structure can support any data type as a key, whereas objects only support strings and symbols. So even though it looked like we were storing numbers in our map, in reality, JavaScript was coercing those values to strings before caching. Additionally, maps provide several safety and correctness guarantees that are designed for the use case of a key-to-value dictionary, whereas traditional objects make support for an inheritance hierarchy and method calls a priority. And on top of all that, using a map makes our intentions crystal clear to future programmers who happen to read our code. So let's rewrite this cache to use a map rather than a traditional JavaScript object. JavaScript added map to the standard library, but elected not to provide special syntax for it in the language. So rather than using language syntax like the infix in keyword and bracket assignment, we'll be calling methods. We initialize our map using the constructor newMap. Then we check for cache inclusion with the has method, and get the value if needed with the get method. Finally, we store our value in the cache using the set method. This program actually runs 41% slower than the original, so a reasonable argument could be made that we should stick with traditional objects in this particular case. Regardless, we now have a working program. Let's talk about our language of the week. This week, we'll be working in Go. Go is a statically typed programming language designed at Google and initially released in 2009. Go markets itself as a faster, more modern C++, and its design prioritizes networking and concurrency capabilities. At its most basic, Go derives its syntax from the Java family, using braces to delimit functions and blocks, and dot notation for module-qualified calls. but the differences start to show quickly. For instance, declaring a variable is done with the var keyword, similar to JavaScript. We write var, then the name of the variable, and then its type immediately after. We can optionally initialize the variable afterwards. If we don't specify an initializer, we get the default value for the type, which is 0 for numerical types, the empty string for strings, and false for booleans. If we want to infer the type of the variable, we can instead declare and initialize in one line using the := operator, which acts like the var keyword but doesn't require a type. Note that regular assignment to an existing variable in Go is done with the equal sign, just like in C or C++. : is reserved for initializing a new variable with type inference enabled. Branching control flow works in Go about like you'd expect. If statements start with the keyword if, and the body is enclosed in curly braces. Like in Java, the condition of an if statement in Go must be a boolean, not a number or some other data type. The if statement can, of course, be optionally followed by an else block. On the other hand, looping in Go is actually done with only one keyword. The single keyword for is used to implement while loops, C-style for loops, and for each loops all in one. In its simplest form, a for loop simply takes a condition and runs like a while loop in Python or C. That is, the condition is checked, and if it's true, then the loop body runs, and then branches back up to the top of the loop to check the condition again. If it's false, we jump down to the end of the loop and proceed with our code. If all we want is an infinite loop, we can even omit the condition. The bare word for followed by curly braces is an infinite loop whose condition is always true. The second form of for loop looks about like a C-style for loop. We have an initializer, a condition, and a step statement. The init statement, which will usually be a : variable initializer, runs first. Then we check the condition and run the body if it's true. Finally, we run the step statement and check the condition again. As in C, the step statement runs even if a continue statement artificially jumped to the next loop iteration. Finally, a for loop can take a range clause. This behaves like a for each loop in Java, or like for loops in Python. The right-hand side must be of a built-in type which can be iterated, such as an array, a string, or a map. Package-level functions are defined in Go with the func keyword. Functions can take arguments as you might expect, and they can optionally take a variadic argument at the end. Go functions can also return multiple values. Now, when I say return multiple values, your mind might go to Python, where it's very common to return a tuple of values and treat that tuple as multiple disparate values. The syntax of Python is even conducive to this, allowing us to omit parentheses on tuples in many places. But that's not what I'm talking about. Go, like Lua and Common Lisp, truly supports returning multiple values from a function, not as a composite data structure, but as actual separate values. When we call a function that returns multiple values, the context in which we call it must be prepared to handle that many values. For instance, we can pass the result of a multi-valued function as the sole parameter to format.println, since it takes any number of arguments and prints them out. We can also destructure the values immediately into different variables, but we can't use a multi-valued function as the condition of an if statement, since the if statement is looking for a single value to test as it's conditional. A common convention in Go is to use multiple return values as an error signaling mechanism. Go doesn't have try-catch statements like Python, Ruby, and Java. So if we have a function that might fail, typically we return two values. On the happy path where everything succeeds, we return the value we care about as the first result and nil as the second. If something goes wrong, we return a default value, such as 0 or the empty string, as the first value, and an error object as the second. Then callers are expected to destructure our return values and check if an error occurred before trusting the result. The type keyword is used to declare new types. In its simplest form, type simply defines a type alias. So for example, if we wanted to define a type called money, which was equivalent to int, we could do so like this. This is simply an alias, so the two types money and int are interchangeable, but we can also declare new structures like this. If we suffix the name of the new type with the keyword struct, we define a new named structure type. We can define a three-dimensional point structure like so. Now we can construct points using the word point followed by curly braces. We can initialize the fields in order, or we can use explicit names to initialize the fields by name. Go positions itself as a light object-oriented programming language, so while it doesn't provide an implementation inheritance hierarchy or any of the sophisticated object-oriented features available in, say, Ruby, we can still attach methods to objects. We can write a method as a function declaration with an explicit receiver, so we can define a dot product or inner product like so, and we call it using the traditional dot notation available in object-oriented programming languages. By the way, now's a good time to interject about Go's naming convention. You'll notice that we named point and dot product in capitalized camel case, while main is all lowercase. In Go, we name exported declarations starting with a capital letter. So point and dot product are exported or public names, which can be accessed from outside our current package. On the other hand, we name private helpers which are local to the module in lowercase camel case. So main starts with a lowercase m, since it's not being exported from the package. This isn't just a convention. This is how Go determines which names are exported from a package. You'll notice we never use the words public or private like we might have done in Java. That's because Go determines visibility exclusively by the identifier's name. One of Go's biggest selling points is its handling of concurrency. Go implements its own form of coroutines branded as Go routines. and we construct a Go routine with the simple keyword go. The go keyword takes a single function or method call as its argument. Here we define a function called print10, which simply prints the numbers from 1 to 10 with the name attached to each printed line. Then we call this function several times in a row from different Go routines, then from our main Go routine. This simple application of Go routines could print out all of our values in any order, but it's not particularly good. There's no synchronization, so the prints could happen in any order. On top of that, if the main function finishes, then all remaining Go routines are terminated, so we might not even see all 40 prints. To ensure we see all the output, we can use channels to signal when one Go routine is done. A channel, as the name implies, is a read-write pipeline through which multiple Go routines can communicate. The make function in Go is used for allocating and initializing channels, slices, and maps. We pass the type of the value we want to initialize as an argument, and make returns a new value of that type. Note that we use colon equals initialization here to avoid repeating the type name, since Go can infer the type of our variable from the make call. Next, we add a channel argument to print 10. When we're done printing out the 10 lines of code, we send our own name over the channel to indicate we've finished. But sending is only half the story. Let's write a function that awaits these messages on a channel. We take two arguments, the channel and the number of messages we're expecting. We loop as long as the count of running Go routines is greater than 0. Inside the loop, we receive a string on the channel. In our case, we don't really care what the string actually is, so we discard it. But in principle, we could have saved this to a variable. Regardless, decrement the Go routine count and continue the loop. Now, down in main, after we spin up our 3 Go routines plus our main one, we wait until all 4 are done. This results in a program that crashes with a fatal error. The reason for that is a fundamental design decision of the Go concurrency model. In the last video, we discussed Elixir, which is another programming language heavily focused on concurrency. But the two languages have very different models of concurrency. This code we've written would actually run if we translated it to Elixir. The reason is that in Elixir, the process is the fundamental tool at our disposal. An Elixir process is a multi-purpose concurrency toolbox. When you spin up a process, you get to run some code of your choice, with a mechanism of communicating with other processes, and a mailbox to store received messages that we aren't ready to respond to just yet. And on top of that, Elixir processes are completely segregated from each other, aside from the process mailbox, which acts as their sole form of communication. In this actor model, the process does everything, and one process can do all of these things automatically. Go is not built on the actor model. Instead, Go decouples all these concepts. A block of code running in parallel is called a Go routine. A mechanism of communicating between Go routines is called a channel. And channels can optionally have a backing buffer which will store any messages being sent without a corresponding receive. Since we didn't allocate a buffer for our channel, any attempt to send a string over that channel will block the current Go routine until somebody on the other end receives it. This means that as soon as the alpha Go routine finishes, it'll block on the final line of print 10. The beta and gamma Go routines will do the same, and the main Go routine will block as well. But the main Go routine is the one responsible for unblocking everybody by receiving these strings. So we have 4 Go routines, and all of them are blocked, waiting on someone else to do something else. It's a classic deadlock, and Go is smart enough to detect it and bail out of our program. If we want a backing buffer for our channel, we simply need to specify its size in the make call. This is the size in elements. So if we ask for a backing buffer of 100, we'll never block on sends unless the buffer already has 100 strings stored in it. Since we're going to be sending a total of 40 strings over the course of our program, this is way more than enough. Now we have a program that prints out all of our messages and correctly waits for all Go routines to terminate. As in the case of Elixir, we won't really need any of Go's concurrency primitives in order to solve Project Euler, so we basically have everything we need now. As a reminder, this was our final solution in JavaScript, which took just over 2 seconds to run. We start every Go file with a package declaration. An executable file, that is one with a main function we can run from the command line, must be in a package called main. Next, we import format, which is where we get our printline function from. Now we need to write our isAbundant function. This function is going to need a map to store our cached or memoized results. First, we check if the value is already in our map. Go doesn't have a separate function to do this. If we try to access a value in a map but assign the result to 2 variables, then Go returns the value in the first variable and whether or not it was found in the second. If the value was not found, the first variable gets the type's default value, which is false since our value type is Boolean. So try to access our cached value, expecting 2 result values. We don't care about the first, so we can bind it to an underscore to ignore it. This isn't a valid variable name. The underscore is a special instruction to Go, telling it to discard that result value. The value we really care about is the second, which tells us whether the key was found in the map at all. If the key was found, then we simply return it. Otherwise, we have to do some extra work first. This is exactly what we did in JavaScript. Sum the proper divisors by hand and store a Boolean result indicating whether or not the sum exceeds the original value in our map. By the way, this conditional pattern is extremely common in Go. Specifically, it's very common to assign some variables and then check the last variable for truthiness, since many functions indicate success or failure using the final result value. Since this pattern is so common, Go programmers frequently shorten it to one line inside the if conditional. Now we've got our caching isAbundant function. Let's write our main function. The first thing we'll do is initialize our caching map. We declared it above, but we never actually initialized it, so we construct a new map from integers to booleans here. Then we loop from 1 up to our limit of 27,948. For each element, try to find 2 abundant add-ins which sum to the value. If we can't find any, add the value to our total. Finally, print the result. This runs in about 4 seconds and solves Project Euler problem number 23 in Go. Tune in next time when we solve problem number 24 in C Shell, a Unix shell language designed to resemble the syntax of C.